All right, we're rolling. How's it going, ladies and gentlemen? Welcome to our team's final presentation of the year. It's been an interesting semester, to say the least. My name is Connor Owens. I'll be presenting DP3 on behalf of Team 3. Our product is the occupancy tracker, and this presentation will cover everything from the initial idea to the final prototype. So, for the last few months, our team has been working on developing a device to track people in and out of a room once you place it near an entryway or a door. This was inspired by the private gatherings restrictions put in place by Virginia Tech and the city of Blacksburg due to the recent COVID-19 outbreak I'm sure you all are aware of. We anticipated initially launching this product in winter of 2020 for students at Virginia Tech, since a vaccine could potentially reduce the demand for such a product. As you can see in this figure, some of the other ideas we had, some of them are not as good as others. We interviewed roommates and fellow students about devices they may have related to this product. This allowed us to compile a list of necessary requirements based on the feedback we received. Excuse me. These are listed in the next slide. These are the interpreted needs that we got from the feedback during the customer surveys. The product needs to be intuitive. It needs to be easy to set up right out of the box. It needs to be lightweight and compact for easy transportation if you wanted to take it with you and use it at a friend's house, for example. It needs to accurately track people entering and exiting a room, because if it doesn't do that, there's really no point. It has to function independently, meaning you can put it on the wall, turn it on, and it will do its job until you turn it off. It also needs to be affordable, because college students aren't exactly known for their massive hoards of wealth. Striking the right balance between all of these requirements is important to ensure the largest possible customer base. This figure represents the main functions of the device, broken down further into sub-functions. As you can see here on this side, the two inputs are power for both the motor and lasers. I haven't gotten there yet, I'm sorry. It has to accept an on-off signal from the user, and of course on the other side it alerts the customer once the maximum capacity is reached. Breaking it into pieces like this allows us to focus on specific processes and get them to work perfectly before we go on. Before coming up with any potential solutions, our team did a search for patents relating to this product. This was done to avoid any potential legal trouble in the future and to get our ideas for our own design. Most of the patents we found simply detected the presence of an individual in a room or tracked the motion of objects in that room, instead of keeping track of how many people there actually are in that room. This image is from a patent filed in 1997. It uses an infrared camera to detect human presences, and then it gives you a ratio of humans detected relative to the size of the room, which I thought was a really cool way of solving a problem like that. I thought it could have been useful for this problem too. Ultimately, we decided that there were no patents that our ideas could be infringing upon, and several methods and sensors found during the search were used in the next step, which is concept generation and selection. We used two methods to generate possible solutions. Each member created 4 possible solutions for a total of 12 potential final designs. The first method was the concept combination table, which can be seen here in the gallery method image. We use the gallery method to get feedback from other team members and students, and we use that to guide our final 6 solutions that we developed using the 3-2-1 method. Once we had our 12 potential solutions, we narrowed it down to the best 3, and these were scored and ranked according to the necessary criteria we found earlier. Based on this analysis, a double laser emitter receiver combination was chosen due to its accuracy and its simplicity. Once we selected the final design, an analysis was done of possible points of failure in our design. This is just one section of the total analysis. Column A here represents the severity of a potential failure, column B represents the likelihood of that failure, and column C represents the ease of detecting or fixing that failure. And then at the very end, the risk priority number, RPN, is a product of all three of those numbers. So the higher the number indicates a greater risk to overall performance. This allows the team to prioritize areas where more development is needed or adjustments need to be made to the design. The most obvious concern found during this analysis were the laser emitters themselves, since they would render the device useless if they were to fail. Because of this, we decided to add a casing around all of the major components of the device to protect them from collisions and misalignments. We also decided to make this casing easily removable to facilitate easy repairs. This is a list of all of the components in our design and their costs. It was created to estimate the total cost of manufacturing this product, as well as estimate the final price of the finished product. The total cost of all of these components comes around to be about $90. However, these values are subject to change as the design process goes on, and we do expect a significant reduction in price if the device reaches mass production. The next slide is the CAD model. This is a rough model of all of the major components of our finished project. As you can see at the top, we have the motor reflector. The reflector is the thing that spins around an LED in the middle and causes a strobe light effect almost, kind of like the light on a fire truck. Below that, we have a 9-volt battery to power the motor itself, and an Arduino which controls the laser emitter receivers and also tracks the number of people coming in and out of the room. Once the maximum capacity has been reached, that Arduino will also turn on the motor, which spins around the lit light. Each of the team members were tasked with creating their own working prototypes. Unfortunately, our original design of a spinning reflector around an internal LED proved to be too unreliable when building the prototype, and it had to be scrapped. Due to this issue, each of the final prototypes uses a motor in a different way to signal maximum capacity. Logan Shepard created a design that causes a loud noise once the maximum capacity is reached. I created a design that spins an indicator flag near the device. And John Mose created a device that reflects the light of an LED in many directions around the room. If we were to redesign this project in the future, we would definitely use a motor that had significantly more torque. It was very disappointing to see that design aspect have to be thrown out. If it actually reaches production, future models could include Bluetooth connectivity to alert the user instead of the use of some light and a spinning reflector. We also talked about having removable and wireless sensors, so you could potentially have an entrance on one side of the room and an exit on the other side of the room, and the device would work just the same. We also got a lot of feedback saying that this device would be very helpful for small businesses or VT facilities, so future models could be marketed directly at those markets. In conclusion, we believe this product is a simple and affordable way to ensure public health and safety, and the engineering design process used for this project can be applied to virtually anything. Thank you all for watching, and please enjoy your winter break.